Hello, everyone. So the topic is now limiting reactants in stoichiometry. Last time we looked at mass-to-mass stoichiometry, and before that, mole-to-mole stoichiometry. And we found out that stoichiometry allows us to calculate the quantities of reactants or products involved in reactions. Now, as it turns out, in real life, when we combine chemicals together, let's write that up here. In real life. Here we go. In real life, when chemical reactants are combined together, it's very rare for them to both be completely consumed. Now, we know that when we mix reactant chemicals together, what happens? The reactants react, and there's less and less and less and less as products form. Do they go down to zero quantities of chemical reactants? Well, the answer is very rare for both of them to go down to zero, to be completely consumed. Instead, something else is far more common in real life. And that is that one reactant is completely used up and the other reactant is not completely used up. So you may remember that the reactant that is completely used up is called the limiting reactant. Limiting reactant. And typically the abbreviation I use for limiting reactant is LR. The thing about the limiting reactant is if it is completely used up, this is the reactant for which there will be none left over after the reaction. So let's write that, none left over after reaction. But the other reactant or reactants in the chemical reaction will not be all used up, not all used up. And what do we call these reactants or this reactant? Well, this is known as the excess reactant in the reaction, and typically I abbreviate this reactant with the abbreviation excess. Get it? Excess. Now, if this reactant is not all used up, that means after the reaction takes place, there will be some left over. Some left over. Let's fix that here. Some left over after the reaction. Left over after the reaction. Okay, well, let's take a look at a real-life limiting reactant example, something we can visualize easily in our heads. And that example here is the building of a bicycle from wheels and frames. So the building of a bicycle could be broken down into two major steps. All right, we take two wheels, attach them to one bike frame, and voila, we make one bicycle. Obviously, that's very simplistic, but it suits our purposes here. So let's make a note of what we're doing here. Let's switch colors. So we have two wheels together with one frame making one bike. Okay, now let's suppose it's your job to build bicycles. Maybe you work at a little bicycle building factory. And every day you come to work and there's a pile of wheels and a pile of frames just waiting for you, all right, to be assembled. So let's take a look at some possibilities before you assemble your bikes and after you assemble your bikes. Before and after assembly. Okay, let's suppose one day, let's call it day one. You arrive to your little factory and you find waiting for you on the factory floor 20 wheels and 20 frames. Okay, so you get busily to work building bicycles. All day long you're building bicycles. And what do you have at the end of the day after you've done the assembly? Well, will you have any wheels left over after you've built your bikes? Well, the answer is no. Every one of those wheels will have been used in assembly. But when we take a look at the frame quantity, we're not going to use all the frames. And that's because if we have 20 wheels, or only 10 out of those 20 frames could have been used to make the bicycles, which means after assembly, we're going to have 10 frames left over. Okay. Now, if we used 10 frames and all 20 wheels, that means at the end of the day, you will have built just 10 bikes. Now, in this example here, since all the wheels were used up, that means the wheels were acting as the limiting reactant. And in contrast, since we had some frames left over, the frames were the excess reactant. We had too many frames for the number of wheels that were provided. Now, let's say you come to your job another day. And once again, there's a pile of frames and a pile of wheels just waiting for you. This time we have maybe 80 wheels and 30 frames. I guess there was a big delivery that night when you were off. And once again, you get busily to work building bicycles. Well, what are you going to have at the end of the day after you've built all these bicycles? Well, will you have any wheels left over, or will you have used all the wheels? Well, the answer is yes, there will be wheels left over. You're going to have 20 wheels left. And why is that? Well, if you have 30 frames, how many wheels do you need? You need 60 wheels. All right. And at that point, you've run out of frames. So we're going to have 0 frames left over. And at the end of the day, how many bikes will you have built? Well, you'll have built 10 bikes. So this is the opposite scenario. In this case, the frames are the limiting reactant, while the wheels are in excess. The wheels are in excess. We had too many wheels. Okay, so this is the basic idea of a limiting reactant problem. Now, what is the significance of the limiting reactant in a chemical reaction? Well, let's get down here. Well, as it turns out, the main significance of the limiting reactant is what it controls. So when a reaction is running, you need both reactants to be present for the reaction to keep going. What does that mean? Well, it means once the reactant, the limiting reactant, is all used up, well, the reaction can't happen anymore. The chemical reaction stops. And if the chemical reaction stops, well, that means we stop making product. So no more product can be formed, and no more excess reactant can react. So, and this is the real key here, this means that the quantity of limiting reactant ultimately controls everything. It controls the amount of product that can be formed in the reaction, and it also controls the amount of excess reactant that gets used. Okay, so let's star this. Little stars here. Okay, well, it's one thing to look at an example involving bikes and frames, which is easy to visualize. It's a whole different story when we're dealing with mixtures of reactant chemicals. And so now let's take a look at how, all right, we could identify the limiting reactant in a mixture of reactant chemicals step by step. So that's our next topic here. So, all right, to identify the limiting reactant. That is very important, identifying it. Well, what do? Well, as a general rule, I always advise students to work with mole quantities because they're easier to handle. So my first step is to always convert all reactant quantities into moles. So let's note here that better to work with moles. Okay. Now, once you've converted your reactant quantities into moles, all right, you're going to designate one reactant, reactant A, and one reactant, reactant B. And you're going to do a calculation, a stoichiometry calculation, where you're going to then calculate the number of moles of reactant B that are required for a complete reaction with reactant A. How? Using the mole ratio. Mole ratio, there we go. Now, once you've done this little calculation, the next step is to do a comparison. You want to compare the amount of reactant B supplied in the mixture to the amount of B that you just calculated using stoichiometry. Now, as it turns out, if the amount of reactant B supplied in the mixture is less than the amount of reactant B calculated, then what happens? Reactant B is the limiting reactant. The opposite is true. That is, if the amount of reactant B in the mixture is greater than the amount of reactant B calculated, well, now reactant B is the excess reactant, which means by default, reactant A is the limiting reactant. Okay, well, now let's see how to put, all right, these steps into practice. So I'm going to go to our second page over here. There we go, second page. So number 21 here says, consider the reaction between iron and water. Iron and water, for which the balanced equation is shown, because we still need balanced equations as always. And our goal is to identify the limiting reactant in each of the supplied reactant mixtures. And we have a mixture A and a mixture B to analyze. Okay, so let's start with the first mixture. The first mixture, 2.5 moles of iron being mixed and allowed to react with 3.25 moles of water. So in this problem, here, let's get a pen back online. Let's consider iron to be reactant A and water to be reactant B. We could have done it the opposite way around. It doesn't matter one bit. Okay, now these quantities are the supplied quantities in our mixture. So the first thing we're going to do is now calculate the amount of reactant B, water, that would react with 2.5 moles of iron. Now how do we do that? Well, we're going to need our good old-fashioned mole ratio. And the mole ratio between iron and water right here is a 3 to 4 mole ratio. So what are we going to do? Well, let's just click back on this. We're going to take my 2.50 moles of iron and apply that mole ratio, all right, which is 4 moles of water reacting for every 3 moles of iron. And when we do this, plugging and chugging, I get 3.33 moles of water. Okay, now what do these quantities represent? Well, this is the calculated amount of water. I calculated it using stoichiometry. Now, this amount of water right here in the problem, that is the supplied amount of water in the problem. Now, what we do at this point is we compare these two quantities. We're going to compare them. Okay. And when we do the comparison, what do we see? Well, we see that the amount of water supplied is actually less than the amount of water calculated. So the amount of water supplied up here is just 3.25. The amount that we calculated is 3.3 moles. Okay. Now, the calculated amount is the amount that we actually need. So we need 3.33 moles of water for the reaction. We only have 3.25 supplied. So in this problem here, we can say that the supplied amount of water is too low. Supplied amount is too low. Now, that means we don't have enough supplied water. So are we going to run out of water? Or do we have too much water and we're going to have some left over? Well, if it's too low, we're going to run out. And if we're going to run out, our conclusion here would be that water in this scenario is the limiting reactant, and iron, by default, is the excess reactant. Okay, that wasn't so bad. Let's do the next one. Okay. In the next mixture, we have mixture B right here, 30 grams of iron mixed with 15 grams of water. So as before, let's make iron A and water B. Now, if we notice this time, the mixture is a mixture with mass quantities, not mole quantities. I don't like to work with masses. I avoid that if possible. So what are we going to do? Well, now we're going to convert these mass quantities to mole quantities. And how do we do that? Well, we divide by their molar masses. So the molar mass of iron is 55.85 grams per mole. And the molar mass of water is 18.02 grams per mole. So we're just doing a little quick mass to moles conversion. And that means that 30 grams of iron is identical to 0.537 moles of iron, while 15 grams of water is really equivalent to 0.832 moles of water. Okay, now we have our mole quantities. I'm going to do my calculation. So using the mole ratio from the balanced equation, starting with iron as reactant A, I know that 0.537 moles of iron in a perfect world, using that mole ratio, reacts with 4 moles of water for every 3 moles of iron. So I'm using that same highlighted mole to mole ratio. And when I do the calculation here, I end up getting 0.716 moles of water. So once again, this is my calculated amount of water, which we're going to compare with the quantity up here, which is the supplied amount of water in our mixture. And once again, we need to compare these quantities. And when we compare these two quantities, this time we see that the supplied amount of water is greater than what we actually need. So this is what we need for the reaction. And when we look at our supplied amount of water, which is the 0.832 moles of water, well, that's more than what we need. So now our supplied amount is, all right, too high. Let's write that here. Supplied amount is too high. And that means, well, we're not going to use all of that water. We have too much water. And our conclusion is that water is now the excess reactant, which means by default, iron would be the limiting reactant. Okay, so a nice simple technique to identify the limiting reactant in a mixture of reactant chemicals. Okay, now, why is it important to identify the limiting reactant in a mixture of chemicals? Well, let's remember, it is the limiting reactant that controls how much product is made in the reaction, and it's the limiting reactant that controls how much of the excess reactant is used and left over. So, now let's take a look at how to apply that with question number 22. It reads, if 0.822 moles of ammonia are combined together with 1.112 moles of copper oxide, and they react together according to the balanced equation below, how many moles of each product are formed and how many moles of each reactant are left over? Okay, so let's begin at the beginning here. So what do we know? Well, we are given an amount of ammonia, 0.822 moles of ammonia, and the amount of copper oxide, that's actually copper 2 oxide, that is mixed with the ammonia. Okay. Now, these are our starting quantities. I like to think of these quantities as our quantities before the reaction has taken place. These are our before reaction quantities. And I should note that, oh, that's a terrible line. Let's try that again. There we go. And let's redraw that line, hopefully a little bit better this time. There we go. Now, I should note that before reaction, there are no products. You don't have any products if nothing has reacted yet. Now, before we can figure out how many moles of each product are formed and how many moles of each reactant are left over, well, our next step is to identify the limiting reactant in that reaction mixture. So let's suppose ammonia is reactant A, copper oxide is reactant B. Well, we're going to do a little calculation. We know we're going to take our 0.822 moles of ammonia times, well, let's apply the mole ratio. Here's the mole ratio. It's a 3:2 mole ratio. And I'm going to abbreviate. 3/2 is the mole ratio. And when I do this calculation, I end up getting 1.233 moles. And this is moles of copper oxide, since I started with moles of ammonia over here. Okay, so this is the little calculation I'm doing to try and identify the limiting reactant. And I'm still pretty horrible at drawing lines here, aren't I? Let's again try and fix them a little bit more neatly. Here we go. There we go. Now, let's remember how we then go about identifying the limiting reactant. This quantity is the amount calculated. This is the amount supplied. So let's just note that this is our calculated quantity. This represents the amount of copper oxide we need. So when we go back and take a look at the original amount of copper oxide, all right, do we have more than we need or less than we need? Oh, we have less than we need. We have less than we need. All right, the supplied amount is what? Too high or too low? It's too low. It's too low, which means that copper oxide is what? The excess reactant or limiting reactant? Well, if the amount of copper oxide is too low, it is the limiting reactant. So let's now add that information in, that this here is now identified as the limiting reactant. So this quantity was too low when we did our comparison. So we compared these two quantities, compare, and this was too low. So that's the limiting reactant. And of course, if that's the limiting reactant, automatically ammonia is the excess reactant. Okay, so now that we've done this analysis, we can finally figure out what do we have and how much do we have of each chemical after the reaction has occurred. Okay, so let's create another little line here. Okay, so let's ask the question, what do we have after reaction, before we get to the question, how much? So let's start with ammonia. Will there be any ammonia present after reaction? Well, ammonia is the excess reactant. So does it get all used up? No, which means that there's going to be some present after reaction. So I'm going to put a little check mark right here. We're going to have ammonia present after reaction. What about the copper oxide? Will we have any copper oxide after reaction? Well, it's a limiting reactant. It gets all used up. So the answer is no, no copper oxide used up. So I'm just going to write 0 moles are present after the reaction has taken place. Now, that takes us to the products. Will there be any products after reaction? And the answer is yes, because reactants react, and what do we make? Products. So I expect all 3 products to be present after reaction. So there should be some nitrogen, check, some copper, check, and some water, check. Well, now that we know what's going to be there after reaction, let's calculate how much of each of these checked substances are going to be present after reaction. And how do we do that? We do that using the limiting reactant quantity. In other words, it is this quantity here, this 1.112 moles of copper oxide, that is now going to be used to calculate everything else. Okay, well, I'm going to scroll up a little bit. Whoops, too high. And let's do that calculation. So if I want to get moles of nitrogen produced, well, where do I start? Well, I start with 1.112 moles of copper oxide. And I'm starting with the copper oxide because it is the, whoops, let's make this red here. This is the limiting reactant. Okay, well, now if I want to calculate the amount of nitrogen, the mole ratio I'm interested in is right here. It's actually a 3:1 mole ratio. So applying that 3:1 ratio, I know that I make 1 mole of nitrogen for every 3 moles of copper oxide. And when I calculate this, I get 0.3707 moles of nitrogen being formed in this reaction. So I'm going to fill that out right here, 0.3707 moles of nitrogen are formed in the reaction. If I want to figure out the amount of copper formed in the reaction, again, I'm going to start with my 1.112 moles of copper oxide. Again, why? It is my limiting reactant. And this time, the ratio that I'm interested in is the 3:3 ratio. So if I apply that 3:3 ratio, 3 moles of copper formed for every 3 moles of copper oxide that react, what do I get? Well, I get 1.112 moles of copper being formed. There's a point right there. So let's write that in here, 1.112 moles of copper being formed. And if I want to figure out the amount of water that is formed, yup, it's going to look just like the previous problem. So again, limiting reactant for copper oxide. What's the ratio we're interested in this time? Well, now the interesting ratio is the ratio between copper oxide, our limiting reactant, and water. So also a 3:3 ratio, meaning that we're again going to get 1.112 moles of water. 1.112 moles of water here. Okay, so these are all the product quantities that are generated in the reaction. But we do have leftover ammonia. So we also need to figure out how much ammonia is left over. So how are we going to do that? Well, the leftover ammonia has to be equal to the difference between how much we started with. Now, how much ammonia did we start with before reaction? 0.822 moles. That is the amount that we started with. Whoops, 0.822 moles. All right, and that was the original quantity. And of that original quantity, some portion is used up. Now, how much ammonia gets used up? Well, that is determined by the limiting reactant. So our limiting reactant, 1.112 moles of copper oxide. Well, how much of that copper oxide actually reacts with the ammonia? Well, we work that out, this time using the 3-to-2 relationship here. So I know that for every 3 copper oxides that react, we get 2 ammonias. There's that 2-to-3 ratio. And what this calculation ends up giving me is 0. Whoops. Let's do this separately here. What this calculation is ultimately going to give us, where again, this is the limiting reactant here, this quantity that we calculate using the limiting reactant is the amount of ammonia that gets used in the reaction. And when I did the calculation here, I got 0.822 moles original minus the calculated amount of ammonia that gets used up in the reaction is 0.7413 moles. And to 3 decimal places, I find that 0.081 moles of ammonia are left over after this reaction. I'm going to write that in over here. 0.081 moles of ammonia end up being left over. Okay. So notice the approach I took with this problem. I started out by looking carefully at what I had before reaction. And since I had a mixture of chemical reactants, I had to figure out which of the 2 reactants was the limiting reactant. And so I did a little calculation to figure that out. Once I knew what the limiting reactant was, I knew that there would be no limiting reactant left over, but I would have products being formed as determined by the limiting reactant quantity, and I would also have some of the excess reactant left over, also determined by the limiting reactant quantity. Okay, let's do another. Let's go to page 3. Here we go, page 3. So page 3, similar problem, but a little bit more complicated. Again, it is a limiting reactant problem. It reads, chromium 3 sulfide may be formed by the reaction between chromium and sulfur as shown in the balanced equation below. And here it is, 16 chromiums plus 3 sulfurs. Note that the sulfur is in the form of S8 molecules. And this reaction takes place forming 8 chromium sulfides. Now, the problem says if 25 grams of chromium are combined with 25 grams of sulfur, we'd like to calculate the mass of product formed and the mass of the excess reactant left over. Happily, we're supplied with all the molar masses we need in the problem to save us time doing this problem. Okay, well, let's begin at the beginning. Well, what do we have? Well, we've got a mixture of our 2 reactants, 25 grams of chromium along with 25 grams of sulfur. Now, these are the quantities that we started with. So these quantities represent the quantities that we're working with before reaction. These are the before reaction quantities. Except I don't like these quantities. Let's remember that I always prefer to use mole quantities whenever possible. So my first step is going to be to convert these quantities into mole quantities. How? Let's divide by their molar masses. Well, we're given the molar mass of chromium, 52 grams per mole. And we're given the molar mass of S8, which is 256.56 grams per mole. Where did I get these values from? Right above in the problem. So when I do this, I ended up getting, what did I get here? 0.481 moles of chromium. And the amount of sulfur I ended up getting here, 0.9. Oops, that's not right. Let's fix that. Let's try this again. I ended up getting 0.0902 moles of sulfur. Now, that's before reaction. Note that there's no product before reaction. Now, again, we have a mixture of reactant chemicals, so before we can proceed, we need to identify our limiting reactant. How do we do that? Well, let's take my 0.481 moles of chromium. And let's now do the calculation whereby we work out the amount of sulfur that should react using that ratio, that 3 to 16 ratio. So times, all right, 3 sulfurs for every 16 chromiums. And that ends up giving me, oh dear, that's this quantity here, 0.092 moles. See, I wasn't looking at my notes very carefully. Turns out, some of you may have already figured out that I did this incorrectly. Oops, let's try get this on. This is not the right amount here. Let's fix that. Sorry. This actual quantity here is 0.0974 moles. My apologies. Okay, now we fixed it. And this represents here the moles of S8, that is, of course, our calculated quantity. Calculated. And of course, what we then do is we compare the calculated amount to the supplied amount. So again, we compare. And what do we see? Well, we see that in the supplied amount, all right, we have 0.0974 moles. The calculated amount is less than that, 0.0902 moles. That means we have too much sulfur in our mixture. And if we have too much sulfur in our mixture, what is sulfur? Well, that means sulfur is the excess reactant. Here, I'm going to stick that here, excess. And by default, chromium has to be the limiting reactant. Okay. Now, once we figured out the identity of the limiting reactant, we can now start analyzing what we have after reaction. Okay, so how are we going to do that? Well, let's start by saying what's there. Well, since chromium is the limiting reactant, will there be any present after reaction? No, it's all used up. However, sulfur is in excess, so we will have sulfur left over, and of course we will also make product chromium sulfide. Okay, so I'm going to automatically note that there are going to be 0 grams of chromium present after reaction. So all we have left to do is figure out how much product is present after reaction and how much sulfur is present after reaction. How do we do that? With the limiting reactant. So we have 25 grams of chromium as the limiting reactant. So now we're going to do mass-to-mass stoichiometry to get from our 25 grams of chromium limiting reactant to the mass of product chromium sulfide. So let's remember how we do that. Our first step in mass-to-mass stoichiometry is to get moles. So 1 mole of chromium for every, well, the molar mass of chromium, 52 grams of chromium. Our next step is to use the mole-to-mole ratio. And in this case, our mole-to-mole ratio is the ratio between chromium and chromium sulfide. So 8 moles of chromium sulfide for every 3 mole, whoops, it's 16 moles of chromium. And our last step, of course, is to get the molar mass of the chromium sulfide worked in, which is 200.12 grams of chromium sulfide. And that's in the problem supplied for every 1 mole of chromium sulfide. Okay. And when we plug and we chug and work this out, I ended up getting 48.1 grams of chromium sulfide are produced in this reaction. So I'm going to write that here, 48.1 grams. Okay. Now, if we want to figure out the amount of leftover sulfur, again, all right, the leftover sulfur is going to have to be the difference between the amount that we were supplied with, which was the original 25 grams, minus the mass of sulfur that gets used. Okay, and this represents the original amount in the mixture. So how do we get the amount used in the reaction? Well, we obtain this, all right, by doing the stoichiometric calculation. And the stoichiometric calculation that we're going to do is going to start with the limiting reactant, which is chromium. Oh, I have just enough room to do that last problem here. So let's do that. So we're going to again start with 25 grams of chromium, which is our limiting reactant. And this time, all right, let's work with black here. This time we're trying to calculate the amount of sulfur that reacts. So first step, convert to moles, 1 mole of chromium for every 52 grams of chromium. In our next step, we're going to use the mole ratio. Now this time, let's just scroll back up here. The mole ratio that we're interested in is the ratio between chromium, the limiting reactant, and sulfur. So times 3 moles of sulfur for every 16 moles of chromium. And last but not least, 256.56 grams of sulfur for every 1 mole of sulfur. And apologies for the handwriting. Well, I plug and chug this out here, and I ended up getting 23.1 grams of sulfur. Now, this is the amount of sulfur used in the reaction. And so to get the amount that's left over, I'll go back here. It's 25, that's the original quantity, minus the amount that gets used, 23.1 grams, or 1.9 grams of S8 are left over. I'm going to write that back in my table, 1.9 grams of sulfur left over. Now, if you were really clever, you might have figured out the amount of sulfur left over, all right, in another much easier way. Okay? And that is by using the law of mass conservation. Notice the amount of chromium and sulfur before reaction, 25 and 25. What does that add up to? 50. Now let's remember the law of mass conservation says total mass before reaction equals total mass after reaction. So, all right, we know that the final masses added together after reaction have to equal 50. All right, well, 48.1 plus 1.9 plus 0, there's your 50 grams after reaction. Okay, pretty neat. So long way or short way, pick your poison. Okay, I know this lecture is going on and on and on. You know, this is probably a good place for you to pause and take a break if you need a break, which I completely understand. But I want to knock this out, so I'm going to keep going. You take a break, come back, and we'll talk about percent yield, but I'm going to forge ahead right now. So, percent yield, the last chapter 3 topic, and you're done for the week. What is percent yield about? Well, percent yield is actually percent yields of products. Percent yield deals with the amount of product formed in a reaction. Now, it turns out we can either make product in a lab, the real life way of making product, or we can use stoichiometry to calculate amounts of product. Well, it turns out whenever a product is produced in a laboratory, meaning that you do the reaction in the lab, you collect the product, you weigh the product, well, the product quantity is then known as the experimental yield of the reaction. Why? Because this is the amount of product you obtained experimentally, experimental yield. Now, in contrast, if you were to instead simply calculate, let's use a different color here, the amount of product, all right, by your step-by-step stoichiometry. Well, if you calculate the amount of product, well, the amount of product that you've calculated is known as the theoretical yield. Theoretical yield of product. And that's because you did it theoretically just using your calculator. No lab work necessary. Now, as it turns out, the theoretical yield represents the maximum amount of pure product that could be formed. So that's the theoretical yield. You can't do better than the theoretical yield. It's just not possible to do better than the theoretical yield. Okay. Now, in the lab, however, when you're actually doing an experiment, making product and collecting product, well, as it turns out, people are prone to errors in lab. And those errors typically lead to loss of product. And as a result, well, what happens as a result? The experimental yield, all right, is almost always lower than the theoretical yield. So experimental yield is less than the theoretical yield in real life. Let's write that IRL for in real life. Okay. And why is that? Well, this is due to, like I said, lab errors. So let's just note that this is due to lab errors. Well, what kind of lab errors am I talking about? Well, they could be all sorts. I don't know. Maybe you've got your product in a beaker and you're stirring with a stirring rod, and some of that product sticks to the stirring rod, and you lose it that way. So some product sticks, all right, to a stirring rod. Might be a way that you lose product in lab. Or maybe when you were mixing your reactants together, which you need to make the product, maybe you didn't notice that some of the reactants splashed out of your beaker. That's also a possibility. So we could say that reactant splashes out while you're mixing chemicals. So, like I said, there are so many different ways that you can make slight errors in lab. Wow. This should say mixing chemicals. Wow. Mixing chemicals. Okay, lots of different ways. Now, turns out that a comparison, and I'm going to go to that last page of this note handouts, a comparison of the experimental yield and the theoretical yield leads to what we're really interested in this topic of this last little lecture here, and that is the percent yield of product. And that is my poor dog whining to be let out of the room. There you go, sweetheart. You're set free. I think she must be really, really bored listening to me lecture about percent yield and stoichiometry by now. She's going to be one smart dog after all this is done. Okay, so getting back to percent yield. How do we get percent yield? We divide the experimental yield by the theoretical yield. So percent yield equals the experimental yield divided by the theoretical yield. And of course, as a percentage, we've got to multiply by 100. In other words, it's a ratio. It's a ratio of what we got in lab. That's the amount of product that was collected in lab. So this is your product mass from lab, product mass from the lab. And the theoretical yield down here, of course, represents the product mass that you calculated. So this is your calculated product mass. Calculated how? With stoichiometry. And we do a ratio. All right, it's a percentage, which is a ratio, to get percent yield. Now, do we want high percent yields or do we want low percent yields in lab? And the answer is we always want high percent yields. So let's note we want high percent yields in lab. Do not confuse percent yield with percent error. We want percent error to be low as possible. Low errors lead to high yields. And in fact, these high percent yields are ultimately evidence of good lab technique. It means that you're losing less product as you follow the step-by-step procedure. So this is evidence of better lab technique. Okay. Okay, well, just one more problem to suffer through, and you are completely done. And that is the last chapter 3 ice problem, number 24. And number 24, the reaction is between carbon disulfide and oxygen, forming carbon dioxide, and this gas is called sulfur dioxide. In part A, it says a student in lab combines 20 grams of carbon disulfide with an excess of oxygen, so thank heavens we don't have to identify the limiting reactant, and ultimately collects 29.2 grams of sulfur dioxide. The goal is to find this person's percent yield. And happily, molar masses are provided for us. Well, we know oxygen is excess, so we don't have to worry about finding the limiting reactant, which means the 20 grams of CS2 are the limiting reactant. Now, what I want to focus on here is this right here, this 29.2 grams of SO2. Okay. Well, what does it say in the problem? That this was the amount of SO2 collected in lab. Now, if this is the amount of SO2 collected in lab, what does this quantity represent? Well, it represents the experimental yield of product. So the problem gives us the experimental yield of product. Now, our goal is to get the percent yield. To get the percent yield, we need both the experimental yield, which we have, but we also need the theoretical yield. So how are we going to get the theoretical yield? We calculate that via stoichiometry. So to get the theoretical yield, so we need the theoretical yield, we're going to do a stoichiometry calculation, a classic mass-to-mass stoichiometry, using our limiting reactant, which we know is CS2. So we're going to do mass to moles, 1 mole of CS2 for every, well, the molar mass of CS2 supplied in the problem, 76.14 grams. Then it's the mole to mole step, and well, let's just highlight those mole ratios. Always a good thing to highlight mole ratios. Here we go. It's 1 CS2 for every 2 SO2s. So 2 moles of SO2 for every 1 mole of CS2 times, well, now we need the molar mass of SO2 supplied for us, 64.07 grams of SO2 for every 1 mole of SO2. And what do we get? Well, I get 33.7 grams of SO2. And this here is our theoretical yield, because we calculated it. So at this point, we can now calculate our percent yield, which was the goal of the problem. And we know that the percent yield is equal to the experimental yield, which was the 29.2 grams of SO2, divided by our calculated 33.7 gram theoretical yield times 100, or in this case, I got 86.6% as the percent yield of this reaction. So really we just have to do a close reading of the problem to make sure we understand which quantity is which. And it was really a key thing to note that that 29.2 grams of SO2 collected in lab represented our experimental yield. Okay, we're almost there. Hang in there. Another student in lab combines with 20 grams of CS2 with excess oxygen, so identical conditions to the first student, but this student obtains a 79.6% yield of SO2. What mass of SO2 did he collect? Okay, so let's start with that right here. What mass of SO2 did he collect? Collect where? In lab. So the goal of this problem is to get the experimental yield. That's what we're really being asked for. What is the experimental yield? Okay. Now, note that the conditions for student, well, let's call this student B because it's part B, are identical to the conditions for student A, in that they worked with 20 grams of CS2 with an excess of oxygen. Well, if they started with the same amount of CS2, which is the limiting reactant, well, the theoretical yield of this student has to be the same as the theoretical yield in part A. So theoretical yield has to also be equal to 33.7 grams because in this case, the same amount of reactant CS2 is used. Let's write that here. Same amount of reactant CS2 is used. In other words, the calculation I did here still is valid, all right, for theoretical yield. Okay, well, we have the theoretical yield, and as it turns out, the problem gives us the percent yield. The problem tells us that this student had a percent yield of 79.6%. Right here. There it is. Okay, well, that means in the percent yield formula, we only have one missing quantity. We know that percent yield is equal to the experimental yield over the theoretical yield times 100. And what do we know? Well, we know the theoretical yield. We know the experimental yield. We're just trying to figure out the experimental yield. Let's call it X. So now what do we get? We're going to get 79.6 equals X over 33.7 grams times 100. Rearranging, what do we get? Well, X is going to be equal to, I get 26.8 grams of SO2 as the student's experimental yield, which represents the amount of sulfur dioxide collected by this student in the lab. Okay. And we are finally, huzzah, huzzah, finished with chapter 3. Take care, everybody. Bye-bye.